Engineering Society and was a sub-team leader or a sub-team lead member of a project team in the College of Engineering. After graduating in 2018, he joined the PhD program at UC Berkeley, where he continues to do research and teach courses on topics such as particle physics and data analysis. So without further ado, please welcome Kenny.
Thank you, Vikram. Apologies to those on Zoom. You may not be able to see my laser pointer. That being said, those of you in the room may also struggle to see my laser pointer. So I'll do my best. So yes, today what I'm going to do is talk about the coldest cubic meter in the known universe, the CUORE experiment. So the first thing I want to do, I'm not going to assume that anyone here knows anything about nuclear physics. Okay, I'll assume that you know that nuclei exist, that protons and neutrons and electrons exist, but really nothing beyond a high school level understanding of nuclear physics. So for those of you who are familiar with radioactivity, we have 3 different types of radioactivity that we deal with in nuclear physics: alpha decay, beta decay, and gamma decay. I'll be focusing on beta decay for this. So what is beta decay? It's this process where you have a nucleus and it has an atomic number, Z, and it has an atomic mass, A. We're going to use these numbers a lot. In beta decay, one of your neutrons in this nucleus, the neutron is slightly heavier than the proton, and it's energetically allowed to decay from a neutron into a proton and an electron. So we go from Z to Z plus 1. That brings the charge of the nucleus up by 1. But to conserve charge, we also need to emit an electron. Now, there's also a funky quantity out there. It's kind of like charge. We think it needs to be conserved in the universe. And it's this quantity called lepton number. So the electron is what we in particle physics like to call a lepton, or what we do call a lepton, regardless of if you like it or not. The neutrino is also a lepton, and this little line over the nu here represents that it's the antiparticle, the antiparticle partner of the neutrino. We just call it an antineutrino, nothing fancy there. So in order to conserve this lepton number quantity, an electron is emitted. That's a lepton, so that's 1. So we also need an antilepton, which is this neutrino, this antineutrino, to cancel out the lepton number-ness. So we think so far that this lepton number here is a quantity that's conserved in nature. But if you go and you read about the standard model and say, okay, from all of the first principles and all of the math we have, why is that? No one knows. It's in what we call an accidental symmetry of nature. So perhaps it's not really a good symmetry. So there's this proposed process, which we've never observed in nature, called neutrinoless double beta decay. And that's really at the heart of what we're searching for in CUORE. So we'll start with just what is double beta decay. Well, I took the diagram from the last slide and I've made another copy of it and I flipped everything around. So it's literally just 2 beta decays happening at the same time, where you emit 2 electrons, 2 antineutrinos, and you have 2 nuclei that go from Z to Z plus 1. Pretty straightforward. But now let's look on the right. I've drawn this diagram in a suggestive way to put these 2 neutrinos close together, because in neutrinoless double beta decay, the idea is that this neutrino is never actually emitted. Instead, it's what we call in particle physics a virtual state. A virtual state just means a way to write down a process that's mediated by something, but that something never actually shows up in nature. You can't actually go and measure the virtual particle. It's really just a mathematical tool. But this can only happen if this antineutrino on the bottom and this antineutrino on the top can annihilate each other. You could think of a proton, or sorry, a positron and an electron, or any particle and antiparticle pairing. You put them together and they can annihilate and just produce photons or energy or something. So this could be possible, but only if the neutrino were its own antiparticle, so that it doesn't matter if you have a nu bar or a nu, you can just have this exchange. And we don't know that that's the case, but it's possible that that's the case. So this is a lot of math and a lot of numbers here. And to be honest, it's nothing more than a polynomial in terms of these quantities that I defined earlier, like A and Z. N is a new one. N here is the number of neutrons in your system. So Z plus N will always give you A. Right? The number of neutrons, the number of protons has to be the total atomic mass of your nucleus. So why do we write this down? Well, we can make some approximations. So for example, this term here, this is your QQ over R from E and M, the Coulomb potential, and you're just adding up all of the protons as they interact with one another electronically. You include some things like a volume term and a surface term, which try to get at the sort of large scale behavior of the strong force. But really the things that are interesting to us are these asymmetry and parity terms. And I want to talk about these a little bit and why the heck they're there. Let's look at this asymmetry term. So it's measuring the difference between A and 2Z. So let's think of something like carbon 12, where you have 6 protons and 6 neutrons. So A is 12, Z is 6. So A minus 2Z is 0. So that carbon 12 nucleus with 6 and 6, that asymmetry term is 0. Why do we care about an asymmetry term? Well, we can construct a diagram that looks sort of like this. So let's say I've got an unstable isotope. It's going to go through what we call a decay chain. It might decay to some isotope, but that isotope might also not be stable. So then I should stay by my computer where the microphone is. Then it can decay to something else that's also not stable, and it's just going to cascade down this long chain until it actually hits something that's stable. And so we can try to get at that looking at this plane. So something to note on this plane here is this is all beta decays. So the A value of your nucleus is never changing, right? You always have a neutron going to a proton, or for these red arrows, you actually have the opposite, where you're having what's called an electron capture. So instead of emitting that electron, you're capturing an electron, and then that neutron is getting converted to a positron, or sorry, is getting converted to a proton. So you'll move along, you can move along this these axes while staying fixed in the plane of Z equals 1, or sorry, A equals 130. So let's say you started with selenium 130, and then you decayed to, I can't even remember what SB is, antimony or something. Antimony. Okay, great. I can remember some things. And then this will decay to tellurium 130. Now, something really interesting happens with tellurium 130. After tellurium, the next thing that you want to decay to is iodine 130. But it turns out that there's an asymmetry here. So tellurium is element 52, so its Z is 52. And the number of neutrons in it is, well, what's that? 78, lots of neutrons. So you have a very high asymmetry term. What that does is it can prevent you from actually being able to go to the next isotope that you'd want to. In this configuration, if you were to add one more proton and take away one more neutron, that would actually be energetically not favored, which is weird, because usually we think, okay, beta decay is always going to result in something that's a little bit lower mass, and so it should be energetically favored the whole time. Here, it's not. When I say energetically favored, I just mean, do I have enough energy to get into that final state? Take a ball and roll it down a hill. Is it ever going to get up past where you rolled it due to gravitational potential energy? No, you don't have enough. So you can't get to here from here. You can't make that jump. So instead, you'd have to double beta decay and go right to xenon 130. That's nice for us, because that means that we don't have a single beta decay background to worry about. Single beta decays are, if they're allowed, will always dominate double beta decays. They're just way more likely to happen. So we need to pick isotopes like this, which have this sort of weird effect. Once we've picked out one of those, what do we do with it? Well, we go and we measure the beta decay spectrum. Now, beta decay actually played a really important role in the history of particle physics in general, because beta decay, we originally, back in the day as physicists, thought that this should happen at a particular energy. Take the difference between your first isotope and your second isotope, your parent and daughter, as we say, or parent or child, doesn't matter to me. You would expect all of that energy to be shoved into the electrons, which would put a nice peak right here at what we call the Q value. That's just the difference in energy between the two nuclei. So you start with some energy, you lose some energy, it's got to go somewhere. It should all go into the electron, right? Well, it didn't. And you had this nice spectrum. And people were coming up with crazy theories. They were saying, maybe conservation of energy is wrong. And when serious theoretical physicists are grappling with maybe throwing away conservation of energy, you know something big is about to happen. The actual explanation for this was the existence of the neutrino, because now you can share that energy between the electron and the neutrino, and you can produce this spectrum. But what did we say about neutrinoless double beta decay? By definition, there aren't any neutrinos. So you're going to have to get what people thought they would get back in the day, which is this spike right here at the Q value. That's our experimental signature. If we see a peak here at the Q value, which we know, then we know that a neutrinoless double beta decay happened. So the goal is just to measure this peak. And yes, it sounds simple, but this is not drawn to scale. This peak here, well, we don't even know if the process can happen. It's just theorized. But even if it could, we've put limits on this that are more than 10 to the 30 years when it comes to the half-life. So even if you are going to see it, you're not going to see it very often, and you're only going to have a few events in this peak. So that's where all of the challenges are. How do you actually go about finding this peak? Given that you're in the real world, you have background, things are messy. We live in a post-nuclear war, a post-nuclear world. Let's hope. And that means that you have background radioactivity that's like a lot higher than it used to be before 1941 or 1945. So that's a challenge. But even so, physicists are working on this, myself included. So just to really emphasize this, let's take an example where A equals 16, where you have 8 protons and 8 neutrons. You can think of the y-axis of this graph on the left as being like an energy of each ball that you want to put in there. And you can see that, well, let's put in our 6 protons, and then let's go ahead and put in 8 neutrons. If I want to now shove in 2 more neutrons, I'd have to put them in a higher energy configuration than I would put the next 2 protons, because the protons and the neutrons live on different energy ladders. It's kind of like electrons. You can't just shove arbitrarily many electrons into a single atomic state because of Pauli's exclusion principle. Same exact thing here. You can have a spin up and a spin down proton in one energy state. I can put a spin up and a spin down neutron in the same energy state. After that, I got to go to the next highest energy state and start building a ladder. And it's this asymmetry that can give you something that we can take advantage of, where you can have a double beta decay. So on the graph here, this is just another way of demonstrating what I showed before, where you've got some particle or some isotope that's energetically forbidden to decay via a single beta decay. So it has to decay via a double beta decay. And one fun fact is that you'll only see this phenomenon happen in so-called even nuclei, where there's an even number of neutrons and an even number of protons. So why are we doing this? Like, why do we actually care? There are a lot of really interesting physics ramifications for this. First of all, as I said before, just the fact that we would discover that the neutrino is its own antiparticle, that's cool. That's something new about the standard model. But we can go deeper. So I would like you all to, again, I'm not going to assume that you know anything about particle physics, but in our day-to-day lives, we know that particles have mass, right? We're here, we can touch stuff, things are heavy. How does that happen? Think back to maybe in 2012, you heard about this discovery of the so-called God particle, the Higgs boson. I hate that term. It's very bad jargon, but it caught wind in the popular media. This Higgs boson effectively tells us how we can get masses for all of the different particles. And the way it works is that each particle comes in two different fields, two different states. One's left-handed and one's right-handed. For those of you who know what it means for a particle to have chirality, great. If you don't worry about it. Let's just assume that there are two different hands for a given particle, two different handednesses. Now, what the Higgs boson does is it takes that left-handed field and it takes that right-handed field and it puts them together. So for those on Zoom, I'm shaking my own hand right now. And I wanted to use the analogy of a handshake, but I realized that's usually two people's right hands. So I'm going to sit here like an idiot and shake my own hand. This is what the Higgs mechanism does. It takes the left-handed field and the right-handed field and it couples them together. And that gives us what we call a Dirac mass. But nature is a fickle beast and really likes to mess with us, especially as physicists, because we think we know something about nature and then we get a curveball thrown at us. Neutrinos don't have a right-handed component. They're only left-handed. They're the only particles that we know of that do this, that have mass. And we know that they have mass based on experimental data collected by the Snow and Super K experiments, which won a Nobel Prize later. I want to say 2011 or something, but within this century. My roommate would be upset that I don't know that off the top of my head. But on the flip side, antineutrinos are only right-handed. They're never left-handed. So it seems like this weird sort of situation. And it would be quite parsimonious if really the right-handed neutrino and the left-handed antineutrino were two manifestations of the same thing. And we as particle physicists are just not thinking of it that way. And there are ways to do this. We could do a couple of things. First, we could introduce some mechanism that's outside of that Higgs mechanism that I mentioned earlier, that would only rely on left-handed fields. This typically involves what we call a Majorana mass term. I'll get into that a little bit later. On the right, I've drawn another possibility where maybe there's some unidentified particle that's really heavy or really hard to detect, or both, that can couple to the neutrino, but it doesn't really like to couple to anything else. We might call that a sterile neutrino. There are all sorts of theories out there that describe different possibilities, but in order for us not to have seen it already in colliders and other experiments, it's got to be pretty darn elusive. So we don't really know which of these is the case, but regardless, we can do some explorations just to see if the neutrino is its own antiparticle, then one of these has to be the case. So we should build the experiment and see if we can even identify that that is what's going on. Now, I'm going to pull back the curtain a little bit and dive into a little bit of the math. Again, if you do not know what something like a Lagrangian is, that doesn't matter. I'm just going to step through sort of bit by bit what's going on here. So these two new things here, this nu bar nu, so you've got a left and a right plus a right and a left. That's typically what you expect to see for this Dirac mass term, right? It's this handshake of the left hand and the right hand coming together. With this so-called Majorana mass, which was named after the Italian physicist Majorana, he showed that actually I could write down a perfectly good mass term where I don't have any subscript r's. I'm just using subscript L. So I have the left-handed field coupling to itself. And so by rewriting some of the equations and making some assumptions, now what we call the Majorana condition, we could actually get a mass out that is just from the left-handed neutrino. And how would you actually get a mass? Well, you can take the Dirac mass term and the Majorana mass term. You can throw them into a matrix. You can do what's called an eigendecomposition. Basically find the two values of the matrix that are most important. And you're going to extract one term here, which is what we call the right-handed mass term. You'll also get another term here, which is this this Dirac mass that I talked about earlier, squared divided by that big mass term. Why did I just call it a big mass term? I think I just spoiled the punchline. Well, neutrinos are really, 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 really small compared to everything else in the standard model. Sub-electron volt per c squared. The next lightest particle in the standard model that we know of is the electron. And that's like half of a mega electron volt. So way different orders of magnitude in scale. And physicists don't really like that. That's not really what we would expect. We like when our parameters to the standard model are all about the same size. So perhaps this m sub r, this right-handed mass term, is really, really, really big. There's some particle with some huge mass out there at this scale that we can't observe in colliders, and it very, very rarely interacts with anything, so we've never seen it. But it also comes in the form of this other mass, but it's in the denominator. So if I make this m sub r really, really big, it forces this second value to be really, really small. This is what we call the seesaw mechanism. Thank you, Donnie. Because if you have something that's really heavy on one side of your balance and something that goes as inverse to that something heavy, you're going to get this sort of flipping. So this is an idea that physicists like because it gives us an explanation for why the neutrino masses are so small. And it might also give us an explanation as to why we don't even see any right-handed neutrinos. I want to pause and see if there are any questions here, because this is all of the particle physics, and particle physics is hard. So I want to pause and just make sure that we're all good. Yeah. They do, yes. So the question is, do neutrinos in fact have mass? The answer is yes. For a long time, theorists thought that they didn't, and plenty of people thought that they didn't, not just the theorists. And then there was this problem with the solar neutrino model. We expected so many neutrinos from the sun. We weren't getting that. So why not? Turns out the neutrinos were oscillating between different flavors, and we were only picking out a third of them. And you can only have this sort of oscillation mechanism if there's a mass, right? You have to have a clock. And if you're massless, then your world line is right on the edge of the light cone, and you can't experience time like we think of it. All good? You're welcome. Okay, great. So, oh, right, one more thing. The whole why do we care bit. So no more math, but still some physics. Again, like I said, if the neutrino is its own antiparticle, that's pretty darn cool. That's new physics. That's probably a Nobel Prize right there. The other really cool thing here is leptogenesis. So remember I talked about this lepton number idea? Well, if neutrinoless double beta decay can happen, then I can get 2 electrons out and no anti-leptons. So I've just created 2 leptons for free. This is what we would call leptogenesis. And one big problem right now in modern physics is if you just look at the Big Bang and what we would expect equal parts matter and antimatter. That's a problem because we're here and we're made of matter and we didn't get annihilated with a bunch of antimatter. So how? Well, maybe a process like this, which allows you to create a slight imbalance of leptons over anti-leptons, could do it. And it doesn't need to be a very big amount, right? And so long as the asymmetry is something like a factor of 10 to the 10, 10 to the minus 10, I should say, 1 part in 10 to the 10, then apparently you can build a universe. And that's a question for a cosmologist. But I take their word for it. And that also gives us good reason to go and probe this, because we're trying to answer the quote unquote big questions. So, okay. Hopefully I've convinced you that this is a search worth doing, and plenty of experiments have successfully done the same to many governments around the world. So we have the SNO Plus experiment in Canada, and we have CUORE over in Italy. We are both using tellurium-130 for our isotope of choice. You have EXO 200, Camlan Zen, Gerda, and Majorana. Exo and Camland are both using xenon 136, I believe. Whereas Gerda and Majorana are using germanium 76. So these are just some examples of those double beta decaying isotopes out there. And it's good to search in different isotopes. That way, once we have an idea of if neutrinoless double beta decay can happen, if we make a measurement and we can start backing out real numbers, then we should start seeing it in different isotopes at different rates, and we can confirm our theories that way. So, okay, now I'll talk about the CUORE experiment a little bit. So, first of all, the acronym CUORE stands for the Cryogenic Underground Observatory for Rare Events. In my opinion, it's the best acronym in the game. The upgrade to the experiment that is proposed is called, I don't have it written, but it's called the Cupid Upgrade with Particle ID, aka Cupid. CUORE is the Italian word for heart, so there's also a motif. It's beautiful. I come from a long line of experiments that did not have such great acronyms, by which I mean one other experiment when I was an undergrad. So I'm a big fan of CUORE, and I always make an emphasis to say acronyms are good. Make good ones, spend the time to do it. And I didn't create this acronym, by the way. I'm not giving myself any credit for this. I showed up in 2018, about 20 years after this idea was first proposed. So what is it? It's a bunch of tellurium dioxide crystals. We have 988 of them arranged into these towers. Together, the entire detector mass is 742 kilograms. And like I said, we use tellurium 130. And of the entire detector mass, about 30%, about 200 kilograms, is actually tellurium 130. That Q value I talked about earlier is about 2.5 mega electron volts. And our operating temperatures vary between 11 and 15 millikelvin. And as was alluded to in the title of this talk, this, combined with the fact that the enclosed detector volume is more than a cubic meter, you can do the statistical mechanics and you can say, well, the universe has some fixed temperature, it's like 2.7 Kelvin. And then using what you know about the distributions of photons in the universe, you can say, well, if I took a cubic meter of empty space, what is the probability that the average temperature will be less than 11 millikelvin? And turns out it's much less than the number of cubic meters in the universe. So the probability that you have a random cubic meter of empty space out there that's less than this temperature is very, 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 very small. To the point where we can basically claim that so long as we're below like 60 millikelvin, that we are in fact the coldest cubic meter in the known universe. Unless there are aliens that built an equivalent CUORE that runs at 9 or 10. But that's why we put in the word known. Okay, so a little bit more on the geometry. Again, here's your 1 cubic meter that sits at the super low temperature. Each crystal is about 125 cubic centimeters. And we put them into 19 towers. Each tower has 4 columns, 13 floors. So you can use a deck of cards scheme if you want to label these ace through king. And altogether, of the 988 crystals that are in these towers, we have 980, actually now we're down to 983 of them that are active. But that's a pretty good yield. It's more than 1%, or a bit less than 1% hit. And we've been running now for about 4 years straight. So like I said earlier, we're located here in Italy, under the mountain here, which is actually incorrectly identified as Gran Sasso. This mountain here is called Corno Grande. It's the tallest mountain in the Apennines, or Apennines. And basically, you can just drive right under this mountain. There's a big tunnel sitting on a highway. And then you go on this off-ramp that's sort of underground. And then you can just drive right into the lab. So here is your, I'll use my mouse here. So here's your tunnel. And then you can come right in here and then drive on site and go do your work here on CUORE. This is where I was over the summer, and we're located to a bunch of other dark matter and particle physics experiments like CREST, DAMA, Gerda. I mentioned xenon. I haven't mentioned xenon. Xenon is a dark matter experiment. There are some other neutrinoless double beta decay experiments going on here, like Gerda. So there's a lot of great work being done at LNGS. So why tellurium-130? I should slide my zoom thing over a little bit. There we go. So if you plot that Q value from your the difference in the masses between your different isotopes, you'd want to get this as far to the right as you can. The higher the Q value, the better for you. There are a few reasons for this. First of all, things like thorium-232 and uranium-238. This is why I brought up the fact that we live in a post-nuclear world. These give you a background of radioactivity that is just ambient. You can't do anything about it. Like, there's no way to get it out. It's just going to be there, especially when you're in places like Europe. But even at this point, the nuclear fallout has proliferated all over the world. So you're not going to escape it. So we would like to get this way out here past these different endpoints. Tellurium-130 doesn't actually do a very good job of that. If we wanted to get the perfect isotope, we'd probably use calcium-48. Problem is, calcium-48's really hard to collect, because another thing you can do is look at isotopic abundance. How much does this isotope occur in the natural world? Calcium-48 barely occurs. And yeah, you can enrich, but enrichment is expensive. And as experimentalists, we need to convince governments to give us many millions of dollars to go build these things. And if 90% of the cost is going into isotope enrichment, it's not really the best use of resources for them. Tellurium-130, though, very naturally abundant. It's like 33%. So we can actually use this. And as I showed earlier, the tellurium-130 is only it's about a third of our detector mass, but we don't do any enriching whatsoever. Our enrichment costs are 0. We just need to make a crystal out of it with oxygen, and then we're good. So you can use some of these other isotopes. Like I said, you can use germanium-76. You can use xenon-136. For Cupid, we are looking into using molybdenum-100. And these things, yes, you do have to enrich them, but there are pros and cons of using them. Molybdenum-100, for example, sits nice and high outside of this endpoint of radioactivity at the gamma line. Oh, if I said thorium, this should say thallium. So sorry about that. At 2615. Okay, achieving low temperatures. So how the heck do we actually go about fabricating the coldest cubic meter in the known universe? I won't get into the details, but it's using what's called a dilution refrigerator. So you use a mixture of helium-3 and helium-4. You ever put oil and water together and shake it up, and you get nice little bubbles, but then eventually it all separates again? Yeah, helium-3 and helium-4 in their liquid forms behave almost exactly the same way. It's because one's bosonic and one's fermionic. For those of you who are good with the different statistics or who have taken your stat mech. And so they obey completely different statistics, and they don't like to mix. We can take advantage of that so-called enthalpy of mixing to get this cryostat down into the crazy low temperatures that we actually can achieve. In principle, if you just looked at the phase diagram for helium-3 and helium-4, you could drive that all the way to absolute 0. But of course, there are experimental limitations you're going to run into before that. But still, you can get down to like 0.01 Kelvin. And then how would we actually go about reading out the signals, right? We need to go look for neutrinoless double beta decay in some way, shape, or form. So to each of these crystals, we put a little thermistor, which is going to measure the amount of power that's on this crystal. We also put a little heater here so that we can inject power as we want onto the crystal. That allows us to do things like calibrate or stabilize our system. And you can think of this whole thing basically as a very, very weak thermocouple. So the nice thing here is that the detector is also the source. So the crystal itself acts as both a heat absorber, but it's also where the radioactive events are going to happen, right? The tellurium-130 isotopes live there. So that's where they're going to beta decay. So you'll have a beta decay occur inside of the detector. That's going to heat up the entire crystal. And then that heat is going to get dumped onto this thermistor. And then we can read that out. And then eventually that heat will be dissipated with this Teflon coupling to the copper here. And the copper frame, whoops, the copper frame is effectively our thermal bath, right? It's where all of the heat goes. That's our heat sink. So then what does an event look like? For those of you who have taken circuits, or I think even in physics too, they'll cover it. An RC circuit, right? You get that classic pulse that sort of decays, and you got to go calculate tau and do the RC stuff, and it's annoying. You can play the same game here, but instead of building it out of electrical terms, you build it out of thermal terms. So you have a thermal conductivity, or a thermal capacity and a thermal conductance, and RC is analogous to C over G. A resistance is 1 over a conductance. And so you can create a time constant. Our time constants are about a second, and this is what a theoretical pulse will look like. And so, like I said, we've been running for many years at this point. CUORE, back in 2017, measured its first real pulse. And you can see that's not far off from what you would expect in theory, a nice sort of RC shape. So this event, who knows? It could be an alpha that was in the rock that ended up hitting the detector. It could have been a gamma. It could have been a neutrinoless double beta decay. To actually go and answer that question, you would need to say, well, what is the voltage of this signal? That's an amplitude that you can then map to an energy. But to get from amplitude to energy, you have to stabilize, you have to calibrate. There's a lot of analysis that goes into that. No one, I think, has ever sat down and said, well, where does this particular event lie on the spectrum? So that's an interesting question. Just by looking at it, I would imagine it passes all quality cuts. So it probably was in our latest analysis. I just don't know where it was. Okay, so one thing I'd like to do, I know that we're running short on time, but I'd like to sort of give you a puzzle to sort of get you to think about the units that we're interested in here. They're called exposure. So let's say that I have this block of metal, this block here on the right, and I hand it to you and I say, okay, go tell me if it's radioactive. What might you do? This is an open question. This is not a rhetorical one. You could get a Geiger counter. Lovely. That was the first thing I thought of too. What else could you do? Remember, we're saying that this is pure, I don't know. So it's pure tellurium-130. You might look inside of it for the daughter isotopes, right? If you can tag the products of the decay, then you can say for sure that a decay happened. But what if you do one of these things and you come up empty? Can you say for sure that the material is not radioactive? I held my Geiger counter and I saw nothing. Does that mean that it's stable? I'm seeing skepticism. If it's not, if you don't see anything, why might it still be radioactive? Exactly. You might have a very, very low level of radiation. Another way of saying that is that you have a very, very long half-life, right? It just takes a really long time for you to see anything happen. So how could you get a better measurement? How could you put a better limit on this half-life? Right, the only thing you could do is say the half-life is at least this long. So what might you do to say, to make that number bigger and bigger? Good, you could measure for longer. What else could you do? What if I had a second block? I could look at more stuff, right? More stuff means I'm more likely to see it. So the unit of exposure that we like to use is mass and time slapped together. We just take mass and time, multiply them together. That's our unit of exposure. They both scale linearly in a background-free regime. Together, they scale as a square root. If you have a background, that just comes from statistics. But this is the quantity that basically everyone in the field is using to say how big of a measurement are we making. So in this past year, back in, I believe, April is when we had this published. We published the results for 1 ton year. That's 1,000 kilogram years of exposure. I wanted to go through the units because otherwise this doesn't really make a lot of sense. So you can see our collection campaign started in 2017. We published a result in 2018, and then we took a long pause. We took a couple more data sets. And then after a couple more pauses, right around the end of 2019, serendipitous, I know, because then a pandemic started, we really started collecting data at a fast rate. And actually the pandemic wasn't bad for us because we were operating the detector almost entirely remotely. And when things are quiet, that's good for us. That's good data quality. So this actually wasn't the worst thing in the world. Of course, there were challenges associated with the pandemic. But once we hit 1,000 kilogram years, we went ahead and we published the latest result into Nature this past year. This is the event reconstruction that I was sort of alluding to earlier, where once you have an event, you need to filter it, gain correct it, do some calibration, see if there was any coincidence with something else in a different detector so that you can pick out different topologies. And then we do some quality selections. And then finally, we do what's called unblinding. The name of the game here, once you have all of these pulses, is to go and measure their energies, which is corresponds to the height of the pulse, histogram them all together, and then produce a spectrum. So just think of this as a giant histogram. When people say an energy spectrum, that's typically what they mean. And we're looking for a peak. In this case, we'd be looking for a peak right at the Q value. And this was our result. So this is CUORE's entire spectrum out to 6 mega electron volts. And we've identified some of the radio background that we would see, polonium-210. A bunch of these things, again, are related to nuclear stuff, as in like, nukes, nuclear weapons testing, which has not been particularly pleasant for us. But if you zoom in here to where we would expect to see neutrinoless double beta decay in tellurium-130, we don't see much, but our best fit gives us a very small bump. So it's not statistically significant. And you can see here our rate on the neutrinoless double beta decay is 0.9 plus or minus 1.4 times 10 to the minus 26 years. So the uncertainty, within one uncertainty, we contain 0. So we can't say definitively that we saw neutrinoless double beta decay. And again, I said 10 to the 30 years. I was off by about 1,000, by about 10,000. It's more like 10 to the 26 or 10 to the 25. Oops, that's a duplicate slide. That should say my work. So I will be very brief here, but the work that I'm doing in CUORE really focuses on the signal processing aspect of these pulses. So as I showed before, this, where was it? Oh, shoot, that wasn't a good idea. Where did we actually create a pulse? Here, this pulse here, you see it's not perfect. There's noise in it. And that noise might even have some periodicity to it. That's because we've got a bunch of pumps, fans, other things. There are electrical spikes, right? The wall, when you plug in something, in America, it's a fixed 60 hertz AC. Over in Europe, it's 50 hertz that they use. So that's this big green peak here. And also this smaller peak at 150 hertz, just the next odd harmonic. So there's tons of stuff that's going to give you noise in your system. Here I'm just plotting the power of the noise in a particular detector as a function of the frequency. So you can see you've got below 1 hertz, you've got some activity due to seismics and also resonances in our support structure, which I've shown down here on the right. And then we have these pulse tubes, which if you've been around Berkeley long enough, you've probably heard the classic sound of a pulse tube going. It's quite annoying, but I think I have developed a 1.4 hertz clock in my head at this point in my career. These harmonics of 1.4 here are all due to the pulse tubes. And then, like I said, electrical peaks, and then other stuff like pumps, fans, which spin around with fixed frequencies. It'd be nice if we could get rid of that noise. So we put a bunch of acoustic foam up. All of these lines here are also padded in foam, and that has helped reduce the noise. You can actually talk in this room now without having to shout to hear one another. But even so, it doesn't get rid of all the noise. So the next best thing is to put things that actually measure the noise, like accelerometers, microphones, antennas, seismometers, and so on. What we can then do is build a model where we say, based on whatever we measure in the microphones, the accelerometers, what have you, we can assume that there's an array of transfer functions from each device to the detector, and we can try to predict what the noise in the detector will be based on what we see in these other devices. So here's what these transfer functions look like on the right. And you can see there are these particular values where we're doing a really good job of predicting the noise. So there's 1.4 hertz, there's 2.8 hertz, and then 50 and so on are out here. Then you can do the classic game of take these filters, convolve them with each of your auxiliary devices, and then you can subtract out the noise from your bolometer. So here I've plotted another example power spectrum. In black is the original power spectrum, and then in cyan and red are the denoised power spectrums where we're subtracting out that noise. And you can see that at these, particularly at 1.4, 2.8, and higher harmonics, we really are reducing the noise by a lot. And there are some other cool things in here. So if you plot just the raw time stream before denoising, after denoising linearly, and then after denoising quadratically, you can see a clear improvement in the noise RMS of the system. So as far as the results go, before doing any other analysis, if you just make a histogram of those pulses that we put in the detector at fixed energies, then you can see that the spread before and after denoising, the spread originally is the one in gray. And then after denoising, we improve the resolution of this peak, which suggests that we're building that we have a more precise detector. And typically we can improve the noise in a given CUORE channel from somewhere between 20 to 40%, though sometimes we can do as well as 60%. And then if you then go through all of the analysis chain and plot the noise events as a function of energy, you can still see that our noise resolution goes from 3.5 kilo electron volts down to about 3.1. So it's a more modest improvement. It's about 9%. But this is after doing all of the steps that we've been doing for the past year, and adding in this one denoising step does have a pretty, it's a non-negligible effect on the data. So with that, I'll just allude to the ongoing work here. We're finding ways to incorporate denoising into our calibration data, which suffer from not having a lot of noise statistics. I've been working closely with an undergraduate here at UC Berkeley, Aaron Torres, who's been doing really good work to get that up and running, as well as exploring things like adaptive filtration and some machine learning techniques to improve our denoising. So with that, I'd like to thank the entire CUORE collaboration. I haven't updated the photo since our Zoom collaboration meeting, and you can see that I'm right there looking away from my camera. And I'd also like to thank the group here at Berkeley, a photo of us right outside the Campanile, myself included. So thanks, and I'm happy to take any questions with the negative time that we have left.
Awesome. Thank you so much, Kenny. That was a great talk.
Thank you.
Questions for our speaker, either through Zoom or in person? I have a question. So for all the possible elements you had listed on that plot,
Yeah.
is there an experiment running for each of those elements aside from the calcium 40?
No, at least not to my knowledge. That's a good. So the question was, of all of these isotopes that are listed, are there experiments looking at all of these? The answer I'm going to go with is not today. There have been smaller scale tests, like people, you never sit down and you say, I'm going to build something at the ton scale of tellurium-130, right? You show that it works for one crystal, You show that it works for a set of crystals, so on and so forth, and you scale. And there have been some smaller scale things. I want to say that in selenium there was, but I'm not positive. But as far as like the ton scale competitive experiments these days, it's really tellurium, xenon, germanium, and hopefully soon molybdenum 100.
Okay, cool.
Calcium's also hard because even if you can refine it, how do you make a crystal out of it? It's a
Yeah.
pain.
That's fair.
I saw there was a question on Zoom about throwing two neutrino beams at each other and seeing if they annihilate. That's a great question. And for that, I'm just going to defer to the Dune experiment, which is kind of doing that. What Dune is going to do is shoot a beam of neutrinos at a liquid, I believe liquid argon time projection chamber. And they will do like a year or so of their neutrino data, and then they'll turn on an anti-neutrino beam and then see how the anti-neutrinos interact with the detector and hopefully make a conclusion on neutrino anti-neutrino symmetry that way. Another question here on Zoom: is there any forecast whether CUORE or Cupid can detect a neutrinoless double beta decay or set a limit on its cross section? That's a great question. The answer is yes, and I don't think that I have this plot on me, but let me check. Because there's a nice plot called a lobster plot, which, okay, I'm going to try Googling here. And it shows, yeah, here we go.
Very aptly named.
Yeah, so the reason for it is because this bottom bar here kind of looks like a lobster claw. And what you can do is take elements of the PM&S matrix that have certain bounds, and you can take certain assumptions about the nuclear matrix elements. So these bands here, the reason they have some thickness is because we don't know exactly what the nuclear matrix elements are for something like tellurium-130. Turns out it's really hard to just throw tellurium-130 into a lattice QCD model. So there's uncertainty here, but the idea is that we can push this experimental sensitivity lower and lower by taking more data and getting more and more exposure. So right now we are just starting to get into the inverted hierarchy regime for neutrino masses. And if we can get below this green line, then we can say for sure that both the inverted neutrino hierarchy mass and neutrinoless double beta decay can't happen. So if you're below this green line and you know that the neutrino mass hierarchy is inverted, you've ruled out neutrinoless double beta decay. That being said, the jury is still out on which mass hierarchy is actually the one we live with. So you can't really make that statement. And also, unfortunately, there's this hole here, right? This goes all the way to 0. So just like the dark matter people, eventually we have the problem of, well, we could look forever. Very good question, Robin. Thank you. Anyone else? Wow. Oh, good. Okay.
Not, then let's thank our speaker one more time.
Okay. Thanks for coming, everyone. Please sign in if you can. It does help us out a lot. And yeah, we'll see you next time. Thank you.